Hey guys, welcome back to day 43. We got gas laws today in this video. First, let's define a gas. So what is a gas? And a gas is a state of matter in which atoms or molecules have a great deal of space between them and are free to move relative to one another, lacking a definite shape or volume. A gas conforms to those of its container. So gas is just a state of matter in which atoms or molecules have a great deal of space between them. They're free to move around compared to one another. They don't have a definite shape, they don't have a definite volume, and they conform to those shapes and volume of its container. And you pretty much knew that. You might not have wrote that exact phrase down, but you probably knew that. The next question is, when we talk about gases, how do we measure a gas, right? We're very interested in measurement. How do we measure a gas? Well, solids, if I have a solid, I usually get a mass, a weight. Liquids, I can do mass, I can do volume. Gas, I can do volume, I can do weight, mass. But how do we check our tires? Like how much air is in your tire? What do you do? Well, it would be a pressure, wouldn't it? So we check gas pressure, right? We know that molecules or particles in a gas are in constant random motion. Constantly colliding with themselves and the sides of the container. So we know pressure is force over area, which is a Newton per meter squared, or a PA for Pascal. And we don't use pascals as our standard unit, even though it would be the SI unit. We take that there's 101,325 pascals is 1 ATM or atmosphere. For gases, there's something called STP, which is standard temperature and pressure. The standard temperature for gases is 0 degrees Celsius or 273 Kelvin, not 25 or 20 to 25 degrees Celsius. It's 0 degrees Celsius. And the standard pressure for a gas would be 1 atmosphere. So we know that there's gases and they have this, they exert this force over the area. And if you've ever had the wind knocked out of you, you understand that air is pushing on us and it's hard to breathe when you get the wind knocked out of you because your lungs are being like pushed in, and there's no air in your lungs to help expand. The question is then, how do we measure this the gas pressure? And this was invented in 1643 by a guy named Torricelli. Right, he invented this thing called the barometer. And if you look at the barometer here, we have a vacuum, which a vacuum means there's no matter. So there's no matter. So you see the height of this column here, the height of mercury here to the surface. So all this mercury, that mercury has a mass, so to speak. And that mass is pushing down this way, right, on the surface. The atmospheric pressure is pushing on the surface of the mercury too. And so the atmospheric pressure equals the height of the mercury. So at sea level, under normal conditions, that's 76 centimeters of mercury, or 760 millimeters of mercury, which is 760 torr, which is 1 atmosphere. So those are your conversions. 760 millimeters of mercury is 760 torr from Torricelli, and that's 1 atmosphere. And that's the start of the units for pressure. There's lots of different pressure units out there, but these would be the two we'll use. So you know that 14.7 pounds per square inch psi is also 1 atmosphere. So that's how it's measured. It's also 29.92 inches. So when you look at the pressure, sometimes you'll see this, and that's what normal. So there's higher pressures, lower pressures, whatnot. When we talk about gases, there's 4 relationships we want to talk about when we talk about the gases, and they are A, B, C, and D. A for Avogadro, B for Boyle, C for Charles, and D for Dalton. And Dalton will be in the next video. We'll talk about A, B, and C in this one. Avogadro, that volume is proportional to N, which would be the number of moles. Boyle is that PB equals constant. Charles, that volume is proportional to temperature. And Dalton, that pressure is equal to the sum of the total pressures. And we'll talk about that again in the next video. So let's talk Avogadro first. V is proportional to N. So it's directly proportional. So you could actually have V and B and N and N. N and N. 1 and 2 and 1 and 2. The volume occupied by a gas is directly proportional to the number of moles present. at a constant pressure and temperature. And that's important. So at constant pressure and temperature. So they can't change. Also at standard temperature and pressure, 1.0 mole of any gas, and I'm going to put in there, we're actually going to put another word in there, any ideal gas occupies 22.4 liters. So that's Avogadros principle. So if the number of particles doubles, the size of the particles doubles. That kind of makes sense. Right? But now that assumes that pressure is constant and temperature is constant. And that's Avogadros principle. Boyles Law is that PV equals constant. So pressure times volume will equal pressure times volume. It's constant. So P1, V1, P2, V2. At constant temperature, the volume occupied by a gas is inversely proportional to the pressure. This is squeezing a balloon, right? If you increase the pressure by decreasing the volume, right? Or you increase the volume by decreasing the pressure. So if you push on a balloon, you're reducing the volume, the pressure goes up in the balloon. And if you do it too much, it pops. And if you're 4, this is a big deal. Although, those of you who order things on the web and you get those air packaging, I don't know, they're air package, they're like air bubbles that they're for packaging so things don't slide around and whatnot. Kids love popping those. But anyway, that's an example of Boyles Law. Next one is Charles' Law. And Charles' Law is volume is proportional to the temperature. So as the temperature increases, the volume increases. So at constant pressure, the volume of a gas is directly proportional to the absolute temperature. That means what unit? Kelvin. Because think about it. Can 0 degrees Celsius be in the bottom? No, right? We can't divide by 0. And 0 degrees Celsius to 1 degree Celsius would be an infinite increase in temperature. which means if your tires would ever go from below 0 degrees Celsius to above 0 degrees Celsius, they would infinitely increase in volume. That wouldn't be good, but that doesn't happen, right? Because it goes from 273 to 274 Kelvin. That's why. So now we have these four relationships, well, three of the four relationships, and Avogadro, Boyles, Charles. Let's put them together in gas laws. There are two gas laws that we're going to talk about. There is the combined gas law. We're going to put Charles and Boyles together. There's also another one that we didn't cover but that's okay. It's going to be the combined gas law, and then we'll have the ideal gas law. And so first, let's talk about what an ideal gas is. I don't think we defined what an ideal gas is, have we? All right. So what's an ideal gas? An ideal gas, there were some assumptions made for this ideal gas. And ideal gases, we're going to say that their size is virtually zero. They're points. So it doesn't matter the size, what the compound is. A gas water, gas nitrogen, gas oxygen, or a bigger molecule, like even carbon dioxide, or something even bigger, like when you get gasoline vapor, C8H18, all the same size, which we know is not true, but that they're still very small. We're also going to say there's the attraction. I can spell attraction, ATT. The attraction of the molecules is zero. So that means when two water molecules are in the gas phase, they don't attract to each other. That's an assumption that we're making. That's not exactly true. And also that we have 100% elastic collisions. That means when the gas molecules actually hit each other, there's no loss of kinetic energy. So these are your assumptions. And we're going to be close with these assumptions, okay? These are the ideal gas laws. And the ideal gas law would be, or the combined gas law rather, P V over T. Right? You might notice that we're combining Boyles and Charles' law. P1, V1, and T1 is going to equal P2, V2 over T2. So that's the combined gas law. So I don't necessarily have to memorize Boyles' law or Charles' law. I can just use the combined gas law. And if pressure is constant, I just take the P's out. If volume is constant, I take the V's out. If temperature is constant, I take the T's out. So that's all I have to do. Now, when we talk about the combined gas law, it only works with constant moles. So if the amount of particles of gas are changing, we cannot use the combined gas law. Can't do it. Because we're adding the particles, we're adding a variable that's not there. If we talk about the units here, all right, we have P for units and V for units. The units for P, right? Any as long as P1 equals P2. So if you wanted to use atmospheres, if you wanted to use torr, if you wanted to use PSI, it does not matter as long as the units for P1 are the same as P2. Because if you double the pressure, you double the pressure. It doesn't matter what the unit is. If you half the pressure, you half the pressure. Times 0.25, whatever it is. Likewise for V. Any as long as V1 is V2. So if you want to do liters, milliliters, gallons, it does not matter. As long as they're the same. Again, because if I double the volume, I double the volume. It doesn't matter the units. Temperature. Temperature has to be in Kelvin. Has to be in Kelvin, right? We can't, otherwise, because going from 5 to 10 degrees Celsius does not double the temperature. So temperature has to be Kelvin. So in gas laws, we're always going to be in Kelvin. Otherwise, the pressure and volume can vary. Now we have the ideal gas law. And the ideal gas law is P, right? We're going to P V equals N R and T. That's PV equals nRT. R, there's two R's. So R is the gas constant. And we have to use the correct units. So the R we're going to use is 0.08206. There's another R, that's 8.3145, and that's joules per Kelvin mole. And we use that a lot in Chem 2. Chem 1 year, we're using this R. In this 0.08206, it's liters, atmospheres, moles, and Kelvin. So I think we know what everything needs to be in then for pressure, for volume, for moles, and for temperature. Pressure, of course, has got to be in atmospheres for the ideal gas law. Volume has to be in liters. Obviously, N is moles, has to be in moles. R is the gas constant, and T has to be in Kelvin. So those are our units that we need for these two equations. The difference between the combined gas law is that moles do not change. For the ideal gas law, moles do change. And you can actually get the combined gas law from the ideal gas law, because if you look, if I divide both sides by T, I get PV over T equals NR. So as long as N and R don't change, PV over T equals PV over T. But if N changes, it's no longer PV over T does not equal PV over T because N changed. Now let's do our examples. 2.0 liters of an ideal gas is heated from 50 degrees to 150 under a constant pressure of 1 atmosphere. What happens to the volume? So is this a PV over T? P1 V1 over T1 equals P2 V2 over T2, or is it a PV equals nRT? That's the question. Well, let's look. If I do P1 V1 T1, P2 V2 T2. Do I have a P1? Yeah, I do. It's a constant pressure of 1.0 atmospheres. Do I have a V1? It looks like it's 2.0 liters. What happens to volume? That would be a V2. I don't know. And then T's. I have 50 degrees Celsius and 150 degrees Celsius. I think it's a combined gas law. So I'll have P1 V1 over T1 equals P2 V2 over T2 here. And if we notice, P1 and V1, excuse me, P1 and P2 are both 1, so I'm just going to cross them out. And we are looking for V2 here. We're looking for that guy. So rearranging, I have V1 times T2 all over T1 equals V2. That works for me. So V1 was 2.0 liters. T2, we had 150 down. T1, I have 50 down. That's V2. So V2 is going to be, what, 6? And there we go. And usually in class right now, somebody raises their hand because they caught the mistake. What's the mistake? We left our temperatures in degrees Celsius. All right, how do we get them to Kelvin? We have to add 273. So that's what, 323 and 423 Kelvin. So we come in, that is 423 Kelvin, and that is 323 Kelvin. I did not triple the temperature, did we? So the answer is not 6 liters. Although in a multiple choice test, that would be probably answer C. You take 2 times your 423 and divide it by your 323, and we get 2.6 liters. It's still a big increase, but not a tripling. And there is number 1. And I like number 2 because number 2 piggybacks off of number 1 here. What must the pressure be increased? There's your question. To what must the pressure be increased to at 150 degrees Celsius to reach the volume back its original value of 2 liters? So now we have new conditions. We're changing the pressure. P1, V1, T1, P2, V2, and T2. P1 was 1 atmosphere, and we're looking for P2. V1 now is the 2.6 liters. We raised it 2.6. We want to go back down to 2.0 liters. And temperature is still 150. Well, 150 degrees Celsius or 423 Kelvin. So 423 Kelvin, we'll write that down, same temperature. So it looks like temperature is constant. This one we get rid of it. I have P1 V1 over T1 equals P2 V2 over T2. If temperature is constant, it's gone. And we're solving for pressure, P2. So P1 V1 equals P2 V2. That means P1 V1 all over V2 is equal to P2. So P2 will equal, what's P1? Well, P1 is 1.0 atmospheres. V1 was 2.6 liters. V2, 2.0 liters. So it looks like P2 is what? 2.6 divided by 2. 1.3 atmospheres. And that's the answer to number 2. We got number 3. Sulfur dioxide, right? This, what's going on here? It's a gas that is not what we want as an emission. And we consider it as 1.53 liter sample of SO2 at 5.6 times 10 to the 3rd pascals. If the pressure changes to 1.5 10 to the 4th pascals at a constant temperature, what's the new volume? Do the moles change here? I don't think so. A constant temperature is important. We're looking for the new volume. I have 1.5 3 liters, and we have a pressure of that, and goes to pressure of that. So I think this is a P1 V1 T1 P2 V2 T2. And I have P1 to be 5.6 times 10 to the 3rd pascals, and P2 1.5 times 10 to the 4th pascals. I have V1 being 1.53 liters, and I don't know V2. And the temperatures, we just have them at constant. We have T1 equals T2, and T2 equals T1. So we don't have to worry about them. So my combined gas law, P1V1 equals P2V2. And we're looking for V2. So we know that P1V1 all over P2 equals V2. So V2 would be P1 5.6 times 10 to the 3rd pascals, and P2 1.5 times 10 to the 4th pascals, and V1 is 1.53 liters. Looks like V2 happens to be what? So I have 5.6 times 10 to the 3rd times 1.53 divided by 1.5 times 10 to the 4th. 0.57. 0.57 liters. Wonderful. Number 4. Sample of gas at 15 degrees Celsius in 1 atmosphere has a volume of 2.58 liters. What will the temperature be? Looks like combined again. All right, so we have 1 atmosphere, 1 ATM, and it's still 1 ATM. So 1 atmosphere, it looks like it's constant. 15 degrees Celsius, 15 degrees Celsius, which we add 273. What is that? That would be 288 Kelvin and 2.58 liters. What will the temperature be if this gas is 3.25 liters? That's what we're looking for, T2. P1 V1 over T1 equals P2 V2 over T2. Sorry. Pressure is gone. We are looking for T2. How do I solve? We have V1 over T1 equals V2 over T2. How do I solve for that T2 on the bottom? Well, the first thing I would recommend is to cross multiply. And we get V1 times T2 equals V2 times T1. Right? If I cross multiply V1 and T2 on one side and T1 and V2 on the other. Then I'm going to divide. So T2 will equal V2 T1 all over V1. Okay, so now let's plug in. T2 equals V2, which is 3.25 liters. T1, which is 288 Kelvin. And V1 is 2.58 liters. Okay. So this T2 then would be what here? 3.25 times 288 divided by 2.58. Looks like it's 362.79. I have 3 sig figs, so that's 363 Kelvin. If I subtract 273, that also gives me 89.8. Well, actually, just 90 degrees Celsius. It's quite warm. Number 5. Suppose we have 12.2 liter sample, half a mole oxygen gas at a pressure of 1 atmosphere and temperature 25 degrees Celsius. If this oxygen is converted to ozone at the same temperature and pressure, what would the volume of ozone be? We have oxygen gas, O2 gas, going to O3 gas. And we have 12.2 liters, 0.50 moles, 1 atmosphere, and 25 degrees Celsius. But it's going to O3. And if we look, it's a 3 to 2 ratio, isn't it? If I balance that equation, so we have 6 oxygen atoms on both sides. So the same temperature and pressure. We have the same temperature and pressure. So that means the temperature and the pressure are the same. We're looking for the volume. It will be the volume. We're looking for that. So that's changing. And the moles are changing. So let's look at the moles. If I start with 0.50 moles of O2, we know it's 3 moles of O2 to 2 moles of O3. So that would be what? 0.5 times 2 divided by 3, right? Which is a third with 0.33, right? Half of 2/3 would be 1/3. So we get 0.33 moles of O3. So now we need to do PV equals nRT because the moles changed. I can't just do the combined gas law. I have to do the ideal one. Or no, the pressure is still 1 atmosphere. It does not change. The volume changed. N is now 0.33 moles of O3. R 0.08206 liters, atmospheres, moles, kelvins, and temperature 25 degrees Celsius, which is, you have to add your 273, 298 Kelvin, which that number you probably would just start to associate with 25 degrees Celsius because 25 degrees Celsius is the magic temperature we use a lot, and it's 298 Kelvin. If we do this math, we get to divide both sides by 1 atmosphere, so you take 0.33 times 0.08206 times 298, then you divide by 1. I get 8.1, which is really just 8 liters because we have 1 sig fig. Very good. Number 6, what's the density of methane? Ooh, what's the density? For this, let's jump back to our notes with the ideal gas law and come down here to gas density. Gas density. So PV equals nRT. The units of density needs to be, in this case, grams per liter. Grams per liter. I need okay, so we have atmospheres, liters, moles, Kelvin, and here we have liters, atmospheres, moles, Kelvin. So I can get rid of liters, I can get rid of atmospheres, I can get rid of moles, I can get rid of Kelvin. But I need grams and liters. So I can't get rid of liters somehow. And I can't get rid of... So how do I get rid of these units? Well, we know that moles... If I take the molar mass, grams, if I take grams, the mass divided by the molar mass, we get moles, right? Grams divided by grams per mole gives me moles. So N can be the mass over the molar mass, right? Because, again, density is M over V. All right, so I need M over V. I need the mass over the volume ratio. So let's put in this mass over molar mass. So if I redo this, P, V for volume equals my mass over my molar mass. So I'm going to have mass, M for molar mass. I'll use purple for molar mass. So that M is now molar mass. I use brown right now for mass. And T is temperature. What can I rearrange? M, multiply both sides by M. So that gives me capital M, P, the pressure, the volume, equal to M, R, and T. Okay, now M over V is what I'm looking for. So if I keep my pressure, divide both sides by the volume, pressure, molar mass, equals M over V, R, and T. Well, mass over volume is density, isn't it? This right here happens to be my density. This is density. So that means M over V, or density, will be equal to the pressure of the gas times the molar mass of the gas divided by the gas constant and the temperature of the gas. And so this is my density formula of gas. Which is kind of neat that what's the density of the gas is basically, if they're the same pressure, same temperature, the molar mass. So the heavier the gas, the more dense it is. The lighter the gas, the less dense it is. That's why helium balloons and hydrogen, if you made a hydrogen balloon, which are explosive, helium obviously not explosive, that's why they float in air. Because air is what? Air is mostly nitrogen and oxygen and argon. That's 99% of air. Nitrogen and oxygen, it's more closer to nitrogen. Nitrogen's 2802, oxygen's 32. So it's closer, it's probably a little less than 30 grams per mole. The average density, molar mass of air. Let's just call it 30. It's probably a little less, but let's just call it 30. So anything more than 30 grams per mole sinks. Anything less than 30 grams per mole floats to the top of the atmosphere. It's kind of neat. So now we go back to our example here. What is the density of methane at 1 atmosphere and 27 degrees Celsius? So we have now the density of the gas is equal to the pressure times the molar mass over R and T. Well, density is equal to, the pressure was 1 atmosphere. The molar mass happens to be, well, 12.01 plus 4 times 1.01, 16.05 grams per mole. R, of course, is 0.08206 liters, atmospheres, moles, Kelvin. And 273 plus 27 would be 300. That means my density of my gas would be, I would take my 1, which I don't have to write, 16.05 divided by 0.08206 and divide 300. I get 0.65, 0.65 or 0.7 grams per liter. That would be the volume or the density of my gas, my methane. Number 7. What's the pressure in a 304-liter tank that contains 5.67 kilograms of helium at 25 degrees Celsius? Okay. Well, do we have a PV over T equals PV over T? I don't think so. I think we have a PV equals nRT here. So PV nRT. P, that's the question. What is the pressure? Volume. I have 304 liters. N is 5.670 kilograms of helium. Now we gotta change that to moles, right? Because N is moles. We have a mass. I can take my mass of helium to moles of helium, so that's good. R is my constant. Change color. R is my constant. And T is 25 degrees Celsius, which we know is 298 now. So let's take our kilograms of helium, 5.670. Kilo is times 10 to the third grams of helium. That's an E. Let's try that again. Helium. And we know that 4.00 grams of helium is 1 mole of helium. And so 5,670 grams of helium divided by 4 grams per 1 mole gives me 1417.5, 1417.5 moles of helium. So PV equals nRT. Looking for P. V is 304 liters. N, 1417.5 moles. R, 0.08206 liters, atmospheres, moles, Kelvin, and 298 Kelvin. So that gives me a pressure of, 1417.5 times 0.08206 times 298 divide 304. 114 atmospheres. Now, 25 degrees Celsius, 2 sig figs, it's really what? 110 ATM to 2 sig figs. That's number 7. Almost done. Number 8. At what temperature in degrees Celsius does 121 milliliters CO2 at 27 degrees Celsius and 1.05 atmosphere occupy at a volume of 293 milliliters and a pressure of 140 atmospheres? Okay. Well, I'm assuming that this is going to be P1, V1, T1, P2, V2, T2. I have no moles, and there's no reaction. All right, let's see if we can do this. So now we have the question, at what temperature in degrees Celsius? So we're looking for T2. We have that many milliliters of, why are you erasing? 121 milliliters of CO2. And another volume. We have pressure and a temperature. Okay, what do we have? Do I have a P1? It looks like P1 would be 1.05 atmospheres. And P2 looks like it's 1.40 atmospheres. B1 looks like it's 121 atmospheres. Or sorry, 121 milliliters. And V2 would be 293 milliliters. T1, 27 degrees Celsius, or 298 K, and we're looking for T2. Let's try it. P1 V1 over T1 equals P2 V2 over T2, and we are solving for T2. Cross multiply. P1 V1 T2 equals P2 V2 T1. And again, we're solving for T2 here. So T2 is going to equal P2 V2 T1 all over P1 V1. All right, P2, 1.40 atmospheres. V2, 293 milliliters. And T1, 290, no, not 298. It's 300 Kelvin. 300 K. P1, 1.05 atmospheres. And V1, 121 milliliters. Okay, let's see what we get for T2 in Kelvin. So 1.4 atmospheres times 293 times 300, divide 1.05 and divide 121. I get 969. 969 Kelvin, which if subtract 273, I get 696 degrees Celsius. Very good. Number 9 says a sample of oxygen gas has a volume of 2.5 liters at STP. How many grams O2 are present? Well, this does not look like a P1 V1 T1, P2 V2 T2. This more looks like a PV equals nRT. So a volume of 2.5 liters. We know that. 2.50 liters. STP, standard temperature, we know what that is 273 degrees or 273 Kelvin, pressure 1 atmosphere. So we know we have 1 atmosphere. We don't know N because we're looking for number of moles. R 0.08206 liters, atmospheres, moles, Kelvin, and temperature 273 K. Now, if you want to P, V, N, R, T, feel free to do this. So standard temperature, we know it was 1 atmosphere. The volume was 2.50 liters. N was the question. R, always the constant, and 273 degrees Celsius. So you can do it this way. So if we solve for N, we divide. So for N, I get 0.112 moles of O2. So if I take my 0.112 moles of O2 and multiply that. 1 mole of O2 is 32 grams of O2. We get 3.57 grams of O2. Number 10. An automobile tire at 23 degrees Celsius with internal volume of 25 liters is filled with air to total pressure of 3.18 atmospheres. Number of moles of air in the tire. This looks like a ideal gas law. P, V, N, R, and T. We're looking for moles. Moles is our question. P. Looks like I have 3.18 atmospheres. V is 25 liters. R, of course, is R, 0.08206 liters, atmospheres, moles, Kelvin. 23 degrees Celsius would be what? 296 Kelvin. So PV equals nRT, or N equals PV over RT. So P, 3.18 atmospheres. V, 25 liters. R, 0.08206 liters, atmospheres, moles, Kelvin. And 296 Kelvin. So our moles, and all we want is moles, 3.18 times 25, divide R, and divide by 296. I get 3.27 moles of air. Wonderful. Number 11. A sample of hydrogen gas has a volume of 8.56 liters and temperature of 0 and a pressure of 1.5. How many moles? This is just like the last one. P, V, N, R, T. All right, so P, V, N, R, T. And we're looking for N. So again, N is PV over RT. What is that pressure? The pressure would be 1.5 atmospheres. Do I have a volume? 8.56 liters. R, of course, is R. And R is 0.08206 liters, atmospheres, moles, and Kelvin. And my temperature of 0 degrees Celsius, which is 273. So the number of moles would be 1.5 times our 8.56, divide 0.08206, divide 273. I get 0.573. Do I have 3 sig figs? I have 1.6. So 0.573, 0.6 moles of H2. And that is gas laws. So that's the combined gas law, the ideal gas law, the gas density. You got Boyles Law, Avogadro, Boyle, Charles. So hopefully that makes sense of the gas laws. In the next video, we'll dive into Dalton's partial pressure and partial pressures. And we'll see you then. Take care.